This is Victoria from Digital Nova Scotia speaking. We're very happy to host ACENET today. Ross Dickson is the speaker for today's talk, Solving Big Problems Fast with Parallel Computing. I'm really excited to have you all here with us. I am going to be recording this session, so that'll be available for you after we're done. I'll send over an email. I'll also send over a survey, so if you've enjoyed today's session or have any feedback, please just fill out that survey. It'll inform us on what to put on next for you in terms of programming. And we'll also have the slides available for you that we'll send in that email as well. So fear not, you'll be able to go back and check out all the information again. That's all from me now. We'll be on the chat box. Please, if you have any questions throughout the presentation, use the regular chat box instead of the Q&A, and we'll get to those at the end of the session or throughout if there's a lot of questions coming through. So thank you. With that, I'll pass it over to Ross.
Good morning, everyone. Thank you, Victoria. I'm Ross Dickson. I'm a computational research consultant with ACENET, which is a publicly funded organization that's intended to support research computing in Atlantic Canada. Some months ago, my business development director wanted someone to contribute a seminar to this Digital Nova Scotia webinar series that'd let you know something about what ACENET is without being too sales talky. Parallel computing is one of our core competencies in ACENET, so I said, sure, I've already talked about parallel computing lots, that should be a piece of cake. And then a week or two ago, as the deadline bore down on me, I realized I was going to be talking to a different audience than I usually have, and it's an audience I don't know a whole lot about. So I'm at some risk of saying things today that you already know, or maybe even talking about things that you might know better than I do. I'll try real hard not to say this is the way things are, but instead to say these are some of the things I've learned. And I hope that you can find some nugget here that might be useful to you or at least interesting to you. My usual audience is academic researchers, not in computer science typically, although there are some of those, but mostly in non-computer science fields that make heavy use of computing, which these days is just about all of them. Obviously, everybody uses a computer to do their writing these days, where once upon a time they'd use a pen and paper. But more and more, computers are also used as direct research tools. They're used to make mathematical theories concrete via computer simulation. They're used to reduce massive amounts of data into usable volumes. They're used to produce insight-generating visualizations of these simulations or these data reductions, as the case may be. If those data or simulations are large enough or detailed enough, then it's not uncommon for the researcher to run into the limitations of a single personal computer. Even the extremely capable personal computers we have these days can't keep up with our imaginations of what we might like to do. Moving beyond the limitations of a personal computer is what ACENET's about, and parallel computing is one of the common paths past that. So allow me to honor my academic roots by beginning with the definition. Parallel computing is a type of computation in which many calculations, or the execution of processes, are carried out simultaneously. Large problems can often be divided into smaller ones, which can then be solved at the same time. And that's a pretty darn good two-sentence summary. Props to the Wikipedia contributors who came up with that. But it does remind me of a still older quotation from Henry Ford. Nothing is particularly hard if you can divide it into small jobs. Parallel computing is the art and science of dividing up hard computing jobs into smaller jobs. And it's not a new field, although it is still a very interesting and growing field. So, what can parallel computing do for you? Very broadly speaking, it can do two things. It will either let you get your results faster, or it will let you do new things that you couldn't do before. The new things could be because you can now do more calculations in the same length of time if you're just going faster, or perhaps you can do larger calculations that take up more memory by using multiple computers. There's never such thing as a free lunch. Everything comes at some sort of cost. If you want to use more than one computer, obviously you need to have more than one computer. But computers are relatively inexpensive these days. What's expensive are people and expertise. You need to have the knowledge of how to manage all these small jobs that Henry Ford referred to and coordinate them in order to get the results that you need. So I'm going to start off by talking a bit about hardware, and we'll talk about software afterwards. We can grossly divide parallel computing equipment into three major classes. This is not the only possible taxonomy, but it's the one I find useful. The first type of computing hardware is the shared memory architecture. This is where a number of processors can all read and write the same memory space. These systems are also called multiprocessors, and you almost certainly have one in front of you right now. Pretty much all modern CPUs are built with multiple cores, and each core is, in this model, a processor. Even entry-level consumer equipment. My Intel Core i7, I think, is a quad-core machine that I got last year. The speed at which the various processors can access various bits of memory may be the same, or it may not be the same, depending on the hardware details. If different parts of memory are, different distance from various processors, then we call that non-uniform memory access, or NUMA. Nowadays, it's mostly a specific implementation called cache consistent NUMA, because cache consistency makes it easier for the programmer to work with. You may occasionally in this field see the term SMP, the abbreviation SMP, thrown around. If you want to be really nerdy about it, SMP stood for symmetric multiprocessor, which is the opposite of a non-uniform memory access multiprocessor. But I've seen a lot of articles on the web in the last few years where the term SMP simply seems to be used loosely to mean a shared memory processor. So that's another synonym in this area. From the point of view of parallel programming, parallelizing your problems, the most important thing about a shared memory system isn't how many CPUs you have strictly, not how many actual physical chips are mounted in the motherboard. The important thing is how many cores we've got, which is basically how many simultaneous processes it can support. So while there may be differences, and there are differences in performance and behavior between a machine, say, that says 2 4-core CPUs and a machine that has a single 8-core CPU, in my experience, it rarely pays to obsess over those differences. They're pretty minor and are really only of concern for those who are trying to squeeze every last drop of performance out of some very specific hardware. Consequently, in my business, we generally talk about cores and don't worry too much about CPUs, but because we're focused on cores, we may occasionally slip and say CPUs when what we really mean are cores. We don't usually concern ourselves too greatly about the actual physical chips when we're talking about programming models for parallel programming. Right, so shared memory architecture. Second architecture for parallel programming is distributed memory architecture. The salient feature here is that each processor now has its own private memory bank, and the other processors can't access memory belonging to another processor except by communicating via the owning processor. Since I already mentioned to you that we've all got a shared memory machine of some sort in front of us nowadays, this distributed memory architecture is, in a certain sense, kind of historical or of theoretical interest. But it is worth staring at this diagram for a few seconds longer, just to let it sink in that if the processors can only get at the different information stored in the machine by talking to the other processors, that highlights the importance of the communication between the processors, which we call the interconnect in the business. that communications hardware, the interconnect is key to the performance of the whole system. And we'll come back to this point again later in the talk. Yeah, the interconnect hardware could be Ethernet. There's some pretty capable Ethernet nowadays, or it might be something even faster and more expensive like InfiniBand or OmniPath interconnect. Moving on to a third architecture. The third architecture is really just a hybrid of the first two architectures. We have individual machines, which we also call hosts or nodes, which are shared memory multiprocessors, so multi-core processors, shared memory. And we have multiples of these hosts, which are then connected via interconnect, again, Ethernet, InfiniBand, OmniPath, what have you. And this hybrid model is the way that a modern computer cluster is built, like the computer clusters that ACENET runs and supports. The individual machines are typically highly capable rack-mounted boxes, usually carrying a generous amount of memory, like say 128 gigabytes, and a generous number of cores, like 32 cores or more. And most of our clusters are made with the expensive, very low latency, very high bandwidth interconnect, like, for instance, InfiniBand. Because I know there's always someone in the audience who likes hardware pictures. I've got the obligatory hardware picture in here. This is showing the guts of a cluster. Each of these boxes here with one blue connector in the back is a shared memory enclosure. So as I say, something like 128 gigabytes and 32 cores in there, probably in multiple CPU chips. 2, 3, 4, 5, 6, 7, 8 of such boxes in each row, 2, 3, 4, 5 rows in a single rack. So 40 boxes at something like 32 cores or more is at 1,200 cores just in this rack here. This item here in the middle is a network switch to keep the InfiniBand coordinated. Yeah, ACENET provides access to and support for clusters like this, some of them via our affiliation with Compute Canada. The actual picture you've got in front of you here happens to be in BC. We've got a smaller and more recent cluster like this in St. John's, Newfoundland. I didn't have a picture of it that showed you the guts that I wanted to point at, so I used this picture instead. So if you want to take advantage of parallel computing, either on gear you've already got, or on a cluster like ACENET can get you access to, or on new hardware, or on virtual hardware on the cloud, you will need to think about how to divide your problem into small jobs, a la Henry Ford. In fact, you do very well to think about how to divide your problem into small jobs before you spend any money on hardware, real or virtual. So to that end, let's go on to talk about programming models. And I'm going to talk about programming models by presenting you with 3 example domains that I hope will illustrate the applicability of each programming model. So the first example problem is very much like one that I actually consulted with a grad student about some years ago. The grad student in question had a collection of seafloor images that they'd collected via floater out in the Atlantic somewhere. There were about 1,000 images in the collection. The grad student had written code to quantify objects of interest in the image. It was counting blobs, measuring their size. I don't know exactly what. She didn't try to explain the details to me. But the code that did this quantification on the images took about an hour to an hour and a half per each image. And so you do the arithmetic, an hour and a half per image for 1,000 images is about 1,500 hours. If she sets her personal computer doing this right now, it's going to be about 2 months before it's finished, and in all that 2 months, that computer is going to be busy doing the image processing and not going to be very useful for much else. But this is a great kind of problem to have, because what it consists of is purely independent tasks. If she had 1,000 computers, in principle, she could process all 1,000 images at the very same time. She doesn't have 1,000 computers, but that's okay. She had access to ACENET, and we were able to get her access to a number of computers in one of our clusters, do the same time. This independent task situation, where you've got a bunch of individual pieces and they don't depend on each other, the order doesn't matter, they can run at the same time or they can not run at the same time, it's all okay. This is brilliant. Such a situation can be treated with near 100% efficiency. Essentially, all you need is some kind of software to help you manage all the individual tasks and keep straight which ones are finished and which ones aren't finished, and put all the results back together at the end. There are numerous tools available for this kind of thing. GNU Parallel is perhaps the best known. That works on the scale of an individual computer. Glost is one that's quite popular in our high performance computing community as well. That's a little bit easier to use than GNU Parallel. To scale out to multiple computers, you're going to need something known technically as a dynamic resource manager, more casually known as a scheduler. The scheduler that we're using at ACENET and Compute Canada is called Slurm. It's got nothing to do with Futurama. And there are other schedulers out there like Grid Engine and in the free domain, and things like LFS and PBS Pro in the paid domain. If you're working in the cloud, then things like the Google Cloud Tasks Toolkit will help you manage these sorts of things. And there are lots of others out there. You don't need to do anything with your existing application code. Once the grad student had written the code that quantified one image, that was all we needed to go forward from there, combined with code that we already had. We used a scheduler to manage your jobs from there. This sort of situation is sometimes called parametric parallelism. It's also occasionally called embarrassingly parallel, which is kind of a derogatory term, but we can stand a little bit of derogatory because it gets the job done efficiently. The term high throughput computing is also used to describe these sorts of situations if you're in particular fields of interest. Not every problem, however, can be broken down so simply. So let me go on to a second example type problem, which I've drawn from the bioinformatics field. De novo genome assembly. If you're not familiar with genomics or bioinformatics, then you may not have heard of this. It's a little bit like assembling a jigsaw puzzle, which is why I've got the jigsaw puzzle image here. In genome assembly, the researcher gets typically hundreds of gigabytes of data representing pieces of DNA sequence. You can't read off the whole genome just in a straight line. We don't have the technology to do that. What we have the technology to do is read off a little fragment of, I think up to a couple of hundred base pairs now, maybe 1,000 base pairs. I can't remember where the technology is today. It changes every week. So the researcher gets hundreds of gigabytes of these little fragments, jigsaw puzzle pieces, if you will. And the computer's job is to figure out which pieces go together with which other pieces until it's got the whole picture, the whole sequence. Now, if there happens to be anyone listening to this who is in the business, we recognize the smartest way to do this is to start from a known sequence of a closely related organism, but you don't always have a closely related organism, or you're not sure about that, or there's other reasons why that might not be possible or desirable. So we're talking about the jigsaw puzzle approach here as an example of a type of parallel problem. So if your family has ever put together a jigsaw puzzle, then you probably know that it goes faster with more than one person, parallel processing. But parallel processing of de novo genome assembly suffers from analogous limitations too. Here's a big one. If we have a jigsaw puzzle dumped on the table and I take half the pieces to my room and you have half the pieces in your room, we will not come back later with half a jigsaw puzzle each assembled and we can just fit them together. what'll happen is I'll have to keep getting up from my room with a piece and walking in and saying to you, hey, do you have a piece that fits this one? And it'll go horribly. The process really only works if all the family can see all the pieces of the jigsaw puzzle at the same time. Analogously, all the processors working on a genome assembly really work better if they can access all the fragments at the same time. And if you want that to go quickly, then that means they have to reside in shared memory. This obviously maps very well to the shared memory hardware architecture that I was just talking about a moment earlier. And so this is the programming model. Again, this is not the only taxonomy of programming models, but this is the one that works for me. So this is shared memory programming, also known as multi-threaded programming. Maps very well to shared memory computers. In this model, each process has read and write access to some shared memory area, but to make the programming go more smoothly, each process also has its own private memory area, typically a stack. The processes are sometimes called threads or lightweight processes, LWPs, because that's what threads are, is lightweight processes. And if you don't grok the detailed definition of a process in computerese, do not worry about it. Just understand that when you see the word threads in some article you're reading on the internet, they're talking about this sort of parallel programming model, typically. Programming in this shared memory model with threads, there are lots of tools for that. Two of the popular and long-standing standards are OpenMP and POSIX threads. There are more ways to do this and support in various languages that may be built on top of OpenMP or POSIX threads and they obscure that, or they may make it open. There's lots of tools. Communication between processes is done via the shared memory area. If you're going to be doing your own shared memory programming at a low level, then the programmer has to think about things like race conditions and data dependencies. If two processes try to write to the same piece of memory at the same time, that's a problem. If it matters which order they write to the same piece of memory, that's a problem. And if you want to get really down and dirty about performance, then you also have to think about things like page faults and cache line conflict as well. You probably don't need to get that deep into the weeds, however, because multiprocessors have been a commodity now for several years. You can do an awful lot using parallel libraries and smart compilers. I can really only speak to the tools from Intel for this because that's what I've worked with most recently. But with that caveat, there is multi-threading capability in Intel's MKL math library and lots of other libraries from Intel and others. And the Intel compiler suite for C, C++, and Fortran, and possibly a couple other languages, includes auto-parallelization options, which is basically where the compiler will look at your code and say, I think I can parallelize this segment of it, and do so. The auto-parallelizing compilers aren't brilliant. They cannot match a reasonably well-trained programmer doing explicit parallelization with something like OpenMP. But they are better than a naive programmer taking his first swing at it, and they are cheap and easy to try out as a first step. And they provide a bit of an on-ramp to explicit parallel programming with something like OpenMP as well. A practical limitation of the shared memory or multi-threaded programming model is that it's effectively restricted to a single machine. There does exist software that lets you pretend that several network machines are sharing the same memory. But last I checked, that wasn't particularly performant, and for that reason it hasn't really caught on in that form in my circles. We'll see in a moment that there's a variation on that that is useful. Right, so third example problem, weather forecasting. Weather forecasting is the canonical time-critical programming problem, right? If the weather office takes 24 hours to run their simulations that tell you what tomorrow's weather is going to be, tomorrow's already here and the results are worthless. So the weather office has, from the early days of parallel computing, been a major player in parallel computing. The way that weather is forecast, or one of the components that goes into weather forecasting, I should say, the computer simulation part, is to divide up the surface of the planet into a bunch of little cells, say, I don't know, 10 kilometers by 10 kilometers per cell. I don't honestly know if that's the size they're using these days, but anyway, a bunch of little cells of a certain size, and the computer simulates the temperature and air pressure and humidity and surface heating and ocean cooling and all these things inside each of these cells, and projects current conditions forward into future conditions by doing iterative simulation. Each processor in the weather office's computer cluster may be responsible for one or several of these little simulated cells. And the heat and the moisture and all the rest can move from one cell into its neighbors and vice versa. So these processes need to trade information, and that leads to what we call the message passing model for parallel programming, also known as the distributed memory model for parallel programming. In this model, each process has its own independent memory. It obviously maps very well to computer cluster hardware, as I described earlier. The communication between the processes is, at least at some level, explicit, i.e. the processes will pass messages back and forth between each other. Whether that message passing is needs to be managed by the programmer or not is a function of what tools you're using to do this. One of my old bosses suggested this was a sort of the natural model for parallel programming because, as he put it, you and I don't share memory. We pass messages when we're working together. I'm not sure history has borne that out to be quite as solid as he thought it was, but it's a simple way to think about how you divide up a problem between various processes in a distributed memory model. This obviously has the advantage over the shared memory model that it can be scaled up beyond a single machine and therefore can be scaled up more or less arbitrarily. I say arbitrarily, but just because it can be scaled up without limit doesn't mean it can be usefully scaled up without limit. Efficiency will drop off eventually. And we'll talk a little more about that shortly. The grand old man of message passing programming is a standard called MPI. It stands for Message Passing Interface, and it's an industry standard. It was first published in, I think, 1995. Being 25 years old, it's starting to age a little bit, and if you care to read a critical post about the age of MPI, there's a link here that you can look up in the slides after the talk. Adapting an existing sequential code to MPI is hard work. It involves a lot of rewriting. It probably should involve a certain amount of reconsideration of the whole structure of the problem, because there's just things that are more costly in parallel when you're passing messages that are reasonable to do when you're not, and vice versa. MPI itself has official support in C, C++, and Fortran. It has unofficial support in a variety of other languages as well. But since I've just dumped on MPI for being 25 years old, let me point out that there are other options in multiplicity. And they depend on what other tools you like and to a certain extent on the nature of your problem. Sorry, let me back up a half paragraph here. let me be clear, MPI with 25-year history underlies an awful lot of existing code. I would go so far as to say possibly the majority of the CPU hours that are spent on ACENET and Compute Canada equipment involves MPI programs. And if you are planning, if you can find third-party code that solves your problem that is written with MPI, it's going to work great. There's been a lot of love and sweat poured into MPI code by various people over the years. If, on the other hand, you are starting a brand new large-scale computational project and you have some freedom of choice regarding your software tools, then you might want to look at alternatives to MPI. There is no exact modern drop-in replacement for MPI that addresses some of its age spots, but there are alternatives that overlap in space. The first one I'm going to mention is this is not even so much a standard as a concept called Partition Global Address Space, or PGAS. PGAS is essentially a hybrid programming model, sort of like a sane, sensible merger of the shared memory model I talked about earlier and the message passing model I just presented. So it's a bit of a hybrid programming model. But it's not a Frankenstein. It's very sensible. Essentially, the idea in PGAS is that certain memory is closer to certain processes, and so it tries to minimize the amount of data movement that way. It's supported in a number of languages, some of which you may not have heard of, like Chapel or X10, some of which you have sort of heard of, like Fortran, the most recent, or I don't know if this is the most recent versions of Fortran, Fortran 2008 and later, include support for PGAS programming model. If you're working in a Python shop, I recommend that you look at Dask if you haven't already. Python had initially some intrinsic challenges in going parallel, which have largely been either overcome or worked around as appropriate. And Dask, it seems to me, my impression, take it with a grain of salt, is that Dask seems to be the front runner in useful parallel programming starting from Python. That's combined with other tools like Numba and NumPy and libraries that will do multi-threading behind the scenes as well. If you're in an R shop, I can't say anything nearly so coherent. There are so many choices about how to do parallel computing in R. If you Google parallel computing in R, you will find lots of hits, including one page from the R central software repository that sort of tries to list and give one-line descriptions of all the various projects. It's a little overwhelming, but there are great choices there as well. So a little bit of research there will let you jump from R into using parallel computers quite effectively. There are hundreds, possibly thousands of other projects, tools, libraries, and languages out there that let you take advantage of the growing availability of parallel computing hardware. I personally have neither the time nor the knowledge to do them all justice. So if you happen to know a little bit about this field and I haven't mentioned your favorite tool, please don't be offended. Also, don't assume that I have somewhere in here mentioned what's going to be the best tool for you. As I kind of hand waved earlier, the best tool probably depends to a certain extent on the nature of your problem. ACENET has a mandate to assist not only academics, but also small and medium-sized enterprises in Atlantic Canada with your research computing needs. So if you want some help finding the right tools to scale up, give us a call, contact us, and we'll see what we can do for you. Okay.
Ross?
Yes.
Sorry to interrupt. Just before you go on to the next session, section, there is a question in the queue here. Is there a list of open source software that is pre-installed? Example, WAMPS for molecular dynamics or Keras for NN. Can requests be made for installation?
On ACENET and Compute Canada systems, yes, there is. Probably the simplest thing to do if you have access to one of our systems, well, never mind, even if you don't have access, sorry, this is a public page. The page is docs, docs.computecanada, all one word, .ca. Docs, docs.computecanada.ca. And if you look for available software there, you'll find an enormous list. There's something on the order of 1,000 titles of pre-installed software. I'm pretty sure LAMPS is on it because I'm familiar with that term. If the thing is not on it, then yes, we accept software installation requests. If the software is license restricted, then we need to make sure that all the legalisms are satisfied, but we have done that with a number of licensed pieces of software. And obviously if it's free and open source, then it's just a matter of somebody finding the hour or two to do the install. Okay. There we go.
I just popped that link into the chat for
thanks. Yep. I just opened the Q&A table so I can see what's going on. Excellent. Excellent. Okay, so those are the models. Let's. I'm going to go on now to talk a little bit about the sort of where you should set your expectations if you're moving into if you're trying to scale up with parallel computing. I hope the sound of the neighbor grinding up trees is not coming through my mic. Let's see, speed up, right. You get what you measure. If you're getting into parallel computing in order to do things faster, either faster time to results or more results in the same time, whichever, then you want to think about speed. We'll define a term here. We'll talk about the ratio of the execution time of some parallel code to the execution time of some non-parallel code, sequential code, that does the same thing. And we'll flip that on its head so that bigger is better. That's just the natural way for us to think about things. So if it takes 6 hours to run on one processor, sequential, and 1 hour to run in parallel on some number of processors, then that's a speed up of 6/1, 6. Notice that the amount of speed up is going to be an implicit function of the number of processors you use. It's going to be a function of how the parallel code is written and how the sequential code is written. It's going to be a function of how big the calculation is. All kinds of things are going in there and affecting that number. So speed up is a very specific measure of a very specific case. Ideally, you would hope that your speed up is going to be essentially the same as the number of processors. If you use 2 processors, you'd like to go twice as fast as if you used 1. If you use 16 processors, you'd like to go 16 times as fast as if you used 1 processor. And that's what this straight red line in this graph represents. This is called perfect parallel efficiency. The real world very rarely works that way. More typically, we find that the speed up falls off as you increase the processor count. So this green line represents speed of 14. When you're using 16 processors, we'd call that an efficiency of 14/16 or 87.5%, which is pretty good. We don't sneeze at that. That's pretty good efficiency. It's very common, though, for a parallel program to give consistently diminishing returns, maybe only 55%, maybe only 40% at a certain processor count. Or maybe the speed up just flattens right out and you're getting no benefit at all past maybe about 2 or 3 or 4 processors at the most. It is in fact also exceedingly common to see parallel programs which actually perform worse than their sequential comparator beyond some processor count. In other words, the curve keeps bending down so that there's some processor count at which you get the maximum speed up and then the speed up starts to drop off after that. not reflected in this graph. When a programmer is first learning to think in parallel, you'll even see efforts that can't even match the sequential code at any processor count. So you don't even get this blue line getting up close to 2, that like the line never gets any higher than 1, because parallel programming is not trivial. And if you're a programmer going at it, you have to approach it with a certain amount of humility, at least the first time out, until you figure out how the bits go together and how you actually get performance out of parallel computer. Well, Ross, that sounds like bad news, doesn't it? If you're going to invest in parallel computing, is there any way you can make sure that you're getting one of these high curves here and not one of these low ones down here? Well, let me unpack a little bit of what's going on in this graph. First of all, if these curves look suspiciously theoretical to you, you're right, they are. They're computed from a formula worked out by a guy called Gene Amdahl way back in 1967, hence Amdahl's law. However, I will testify that I have seen experimental performance curves that look an awful lot like these, and I've seen experimental performance curves. By experimental, I mean someone's actually run the program and a different number of processors and calculated the speed up and put the dots on the graph. I've seen curves that look an awful lot like these, and I've seen curves that look even worse. And I've rarely seen experimental curves that look better than this. But there's good news hiding in here. Stay with me. Amdahl's law is built on the idea that you can divide your code into a sequential fraction and a parallel fraction. These little numbers up in the left-hand corner here, 0, 0.1, 0.5, 0.05, 0.10, 0.5, are the sequential fraction of the code. So you get perfect scaling if there's no sequential fraction. You get very good scaling if the sequential fraction is quite small, like 1%. If the sequential fraction is 50%, then it's really not much worth the effort. What is the sequential fraction? That's basically the amount of time that the sequential code has to spend doing stuff that it only does once, starting up, shutting down, reading some global input that all the processes need to know, for example, or anything else that the programmer has not yet gotten around to parallelizing. If it spends a vanishingly small amount of time doing sequential stuff, then you're golden, you're up the top here. Contrary-wise, if you can only find some way to parallelize about half of what your code does, then no matter how many extra cores you throw at it, you're never going to be able to do more than cut the runtime in half, because that sequential part is still going to take as long as it takes, and that's half the runtime, right? So if that's the case, you might as well not bother unless and until you can think of a way to divide up your problem in more of your problem into small jobs. But this sequential fraction, let me emphasize, this is not determined by counting lines of code. It's counting, effectively, it's counting the number of times each line is executed. Really, it's about execution time, not number of lines, but you can think of it as the number of times each line is executed. So think for a moment. If you can usefully run your code on a bigger problem, then maybe the amount of time spent running parallelizable stuff will be greater, and the time spent doing sequential stuff will stay constant, and therefore the fraction will shrink. To reiterate, the time spent in sequential work, sigma in this horrible formula, never mind the formula, the time spent in sequential work tends to stay near constant as your problem size grows. The time spent in parallelizable work usually grows with the problem size, and therefore the sequential fraction shrinks. Now, I'm doing this good news, bad news thing. So here's back to a little bit of bad news. The parallel overhead cost, kappa in this formula, we neglected in those charts. Overhead cost is things like the amount of time spent communicating or coordinating use of shared memory or what have you between the various processes. The overhead cost, the communications, also tends to grow with the problem size. Whether it grows as fast as the problem size or just as some fraction of the problem size, like log problem size, for example, is a great situation to be in. Depends critically on the parallel algorithm that you're using, the way you break up the problem, or the algorithm that's buried in some library you're calling. the overhead cost also depends on the communication speed, which depends on the interconnect, which leads back finally to that thing I showed way back in about the second hardware slide or so, where we pointed out the interconnect that might be Ethernet, it might be something more expensive that's got lower latency and higher bandwidth. So there we are. These are things to watch out for when you're trying to figure out whether your problem is amenable to parallelization and what sort of parallelization it's amenable to. Getting close to the end, I've got a few sort of random notes slides at the end here. They didn't quite fit anywhere else, but I'm guessing they may be of interest to some listeners, possibly. First is GPUs. What about GPUs? GPUs, graphics processing units, are great things. They're basically commodity priced supercomputers, but they are highly specialized. GPUs are basically good for doing arithmetic on huge regular arrays. They're not so hot at if, then, else logic or intricate stuff like that. It turns out artificial neural networks that are doing such stunning things in artificial intelligence or machine learning these days turns out to be just a lot of arithmetic on huge regular arrays, which is why there's this incredible synergy between advances in AI and advances in GPU technology. Programming a GPU at a fairly low level is basically a special case of shared memory programming. A GPU is just a big shared memory unit that's stuffed inside another computer. There are thousands of cores on a GPU, or a GPU can run thousands of threads, if you like to put it that way. However, the GPU shares memory between the GPU threads, but it does not share memory with the CPU in the computer. And all the data's got to eventually get into the GPU via the main memory. So a programmer has to be conscious of where the data is residing at any given point in the program, and should work to minimize the amount of data movement between CPU memory and GPU memory. NVIDIA basically owns this field. AMD is competing with them a little better these days than they were a couple of years ago, but it's still basically NVIDIA is the 500-pound gorilla of the field. If you're interested in GPU programming, I cannot recommend anything more highly than the NVIDIA Programming Guide. Go to docs.nvidia.com and look for CUDA, and there's all kinds of great materials there. ACENET also runs training in this thing. We usually do this in our summer school each year. And if there's already a library or a program, an application written that does what you want to do, for gosh sakes, don't roll your own. Don't reinvent the wheel. There's some really smart people who've written some really amazing code for obviously things like artificial neural networks, for things like molecular dynamics. There's code coming on just these current days for other engineering fields that uses GPUs effectively. So there's lots to be found there. Next random point, cloud computing. I figure my audience probably knows more about cloud computing than I do, since I've had free access to high performance computing clusters since before cloud computing became a thing. You probably already know that cloud services like AWS, Azure, Google Cloud, and so on are a fantastic source of CPUs on demand, and that can save you a lot of dollars and headaches compared to an on-premises solution. All true. If you want to be doing large-scale computing in the cloud, though, be careful about costs. First of all, obviously, CPU costs are kind of right up there and in your face. I have heard more than one story recently about people getting surprised by data movement costs. If your large data problem involves moving hundreds of gigabytes of data onto the cloud and then moving substantial amounts off the cloud later, you're probably going to be paying for that. Read the fine print. Be aware of when you pay for data ingress or egress and how much. And once you're aware of that, you can plan your data movements rationally to not give Jeff Bezos too much more money than he already has. And my final random bit, Hadoop and all that. Have you heard of Hadoop? If you haven't, that's okay. If you have, maybe you were wondering when I was going to talk about it, so it's last random slide. Hadoop is complicated. Strictly speaking, Hadoop is more of a file system than a parallel programming system, but it partakes of both. Data movement is often key to parallel performance. Are you starting to sense a theme? Have I said that line often enough yet? Data movement is key to parallel performance. The Hadoop philosophy was don't move the data to the compute, just do the computing where the data already resides, which was the sort of genius idea that sounds stunningly obvious in retrospect. Hadoop itself was pretty highly specialized for a particular class of problem that Google had, still has for all I know. The term MapReduce comes in here. It was then intended for problems that are susceptible to the MapReduce programming pattern. If you know what that is. If you don't know what that is, you can go look it up. MapReduce, all one word. Hadoop's spiritual successor is something called Spark, Apache Spark. And if you didn't know that already. And Spark is considerably more general and performant than Hadoop, since Spark will keep data in memory rather than writing every bit of it back to disk every time it touches it. Other than, I haven't worked personally an awful lot with Hadoop and Spark. I've done a little bit of sort of hello world kind of stuff, but that was enough to make me realize mostly what I don't know about it. So I can't really give you a really nice guidance over what sorts of problems Spark and Hadoop and MapReduce are best suited for. Large-scale data analysis is a term that frequently comes up. Yes, that some large-scale data analysis is susceptible to MapReduce pattern and hence Spark. I think you can do things beyond MapReduce with Spark, but I don't know exactly what. So I just wanted to acknowledge that this is MapReduce and Spark, and there's a whole, people call it an ecosystem of related tools in this area with lovely names like Flink and oh, I can't even think of any of them right now. So that's out there as well. Right, so takeaways, and if you have further questions, you can be composing them for me as I just reiterate some of the high points I wanted you to take away from this. If you have computing problems and you can find some way to break them into independent tasks where the individual subproblems can be done in any order, don't depend on each other, you are golden. You can scale up quite efficiently. Just need to find some sort of job management software that suits you and go. If you're going to be using a service like ACENET or one of the cloud services, there's going to be job management software already there, sitting there ready for you. You're in great shape. Second takeaway, you have already got multi-core hardware in front of you. And so multi-threaded or shared memory programming applies. And a lot of the things you're using right now actually has some of that under the hood that you're not aware of. Yeah, I see a question there in the chat. I'll come to that in just a second. A parallel computer, as Ken Batcher, he's a computing science prof at Kent State, I think, said years ago, parallel computer is a device for turning compute-bound problems into I/O-bound problems. Data movement, input, output, and communications always have to be top of mind when you're developing parallel computing solutions, even the independent tasks ones. If your independent tasks involve hundreds of gigabytes or terabytes of data, then your biggest problem is going to be wrangling that data to the right place or getting compute to the data or what have you. You need to think about that. And analogous questions apply all the way from there down to GPU level programming and every scale in between. You don't want to neglect what it costs to move data around at any scale. And finally, ACENET can help Atlantic Canadian businesses with their research computing. And I see Michelle has already addressed the question in the chat about the use model for small, medium-sized enterprises. Pricing is based on usage, yeah. There we are. That's all I have to say for today. We can entertain further questions. Thoughts? Oh, that's a good one. Coexistence of parallel. What are your thoughts on the coexistence of parallel computing and quantum computing as problem-solving approaches go forward? Quantum computing is its own highly specialized thing. I think quantum computing will provide, I'm going to use the word magical seeming solutions to a certain very small class of problems. Everyone expects that it's going to just play hob with encryption and public key encryption and stuff like that, which I fear. I expect the experts in the field will find a growing array of other niche problems that quantum computing can solve. I think, like many projects, quantum computing has the feel of being something that's been 5 years away for about 10 or 20 years now. Progress is being made. I'm not expecting it to be relevant tomorrow or next year. Maybe before I retire, it will be relevant. Since I'm sort of moving into old fogey status now, you can take that with the appropriate grain of salt. Parallel computing is a large pool of tools applicable to a pretty wide range of problems. Quantum computing is applicable, well, right now the costs are pretty astronomical. It's applicable to a small range of problems, which will grow slowly as the experts do it. But by slowly, I mean on a scale of probably decades. That's my forecast. I'm not going to put money on that because predictions are difficult, especially about the future. But that's my feeling on quantum computing. Forgot anything else?
Okay, everybody. This is Victoria again from Digital Nova Scotia. Thank you for such an awesome presentation, Ross and Michelle. Wonderful to have you here with us. Like I said at the beginning of the session, I will be sending around an email to everyone that's been in attendance with the link to the slides and a link to the recording so that you can access this information again. If you're interested in hearing more about parallel computing, please do reach out to Ross or Michelle. I'll include their emails in the follow-up email to all of you. So please just feel free to reach out. I think they'd be happy to chat with you about that. If there aren't any more questions, we will finish up today. This is perfect timing. We're at 10:59 at the moment. So thank you once again. Thanks for your participation, and I hope everyone has an excellent rest of their Tuesday.
Victoria, if I could take 30 seconds just to do a plug. As Ross mentioned, ACENET is fairly new to the industry scene, where our history has been academia. So we are really interested in the feedback that you folks here can provide us in terms of any sort of additional training that would be of interest to you, the sorts of services, the sorts of problems, anything that can help us as we refine our offering to industry. So we really look forward to reading the evaluations and any input that you can give us. And as Victoria mentioned, please just feel free to email us at any time.
Wonderful. Thanks, Michelle. Thank you, everybody. I'm going to log us off now, and we'll be chatting soon via email. Thanks, everyone.
Thanks very much for it.
All right, bye.